Welcome again. In this lecture, I will solve the partial differential equations with the help of the Lagrange method. So, solution of partial differential equation using the Lagrange method. Now, suppose that solution of linear partial differential equation of order 1 and degree 1. So, let the partial differential equation is, suppose that this is of the type p small p, q small q equal to some function r, where we know that small p means del z upon del x, q means del z upon del y, and capital P, Q, R are functions of x, y and z. So, now the solution of 1 is some function u, v equal to 0. This is your solution of equation number 1. In last lecture, I was finding the partial differential equation from an algebraic equation. Now in this lecture, I will solve the partial differential equation. So in the last lecture, we have seen that if this was your function, then our solution was of this type. That means of the type equation number 1. So here, if the partial differential equation is of the form 1, then our solution is this one, phi u equal to 0, where u and v are solution of this auxiliary equation dx upon p, dy upon q, dz upon r, and this auxiliary equation 2 is known as, equation number 2 is known as your Lagrange auxiliary equation. So this is your Lagrange auxiliary equation, or you can say subsidiary equation. So the solution of the partial differential equation 1 is phi u comma b equal to 0, or we can also write it as phi equal to some function of v. We can also write it as phi equal to some function of v. So the solution of 1 is either this, or you can write it in this form, where u and v are the solution of this equation number 2, which is known as Lagrange auxiliary equation. Now I will solve the partial differential equation of order 1 and degree 1. As we have a large number of problems, so here I have selected the problems with their types. So let us solve the first type of problem. Solve the first problem is, so first of all I am writing the problems and then we will try to solve these problems. So the first problem is this one, and the second problem is y square p minus x y cube is equal to x z minus 2y, and the third problem is p plus 3 cube equal to 5z plus 10 y minus 3x, and the fourth problem is xyp plus y square cube equal to zxy minus 2x square. So here we have 4 questions, and the fifth one is px z minus 2y square plus is equal to z minus qy, and then multiplied by z minus y square minus 2x cube. So here I will solve these 5 problems. So let us start with the problem number 1. Here you can see that the problem is in Lagrange form. So this is of the type capital P into small p plus capital Q into small q equal to R. So here you can see that your capital P is y square z upon x, Q is xz, and capital R is y square. Therefore, Lagrange auxiliary equation is the Lagrange equation will be your dx upon p equal to dy upon q equal to dz upon r. So this will be equal to dx upon p, that means this is your y square z upon x equal to dy upon q, that is your xz, and dz upon r, and your r is y square. Now say this is your term first, second term, and say this is your third term. Now first let us take second term and third term. So now taking second and third, we get, if we collect these two, we will get dy upon xz is equal to dz upon y square. So this was your y square. Okay. Now here is a problem because we have the x and we cannot solve it with the help of the x. So let us take first and second, then let us see what happens. Now the first part will be dx upon, now this x will go in the numerator, so this will be your x dx upon y square z equal to dy upon x into z. So this z will be cancelled, so we will get x dx equal to y square dy. Now let us integrate this one. So integration of x will be, on integration we get, here we will get x square by 2, then here the integration of y square will be y cube upon 3, then equal to some constant of integration, say it is c1. So this is your first constant. So one set of solution is there, one solution is there, and now we have to find out the second solution. For that, let us take first and third. Let us take this first and third part. Now from 1 and 3 we get, so on taking first and 3 we will get, this was your first, and third is dz upon y square. So again this x will go in the numerator, so we will get x dx equal to, here the y square and y square will be cancelled and we will get z into dz. So on integration we will get x square upon 2 minus z square upon 2 equal to c2. So we have two solutions. So our complete solution of equation number 1, that means of the differential equation, is, therefore solution of partial differential equation is phi. Say this c1 is your function u, because it is in terms of x, y and z. So this will be, the solution will be your f phi of ub equal to 0, where your u is this first term, x square upon 2 minus y square upon 3, y cube upon 3. This is your u, and let us assume this one as v, then we will have x square by 2 minus z square by 2, and this is equal to 0. So this is the solution of the problem number 1. And same solution can also be written as, we can also write it as phi of, we can also write it as u equal to phi of v. So that means x square by 2 minus y square by 3, y cube by 3 equal to some function of x square minus z square by 2. We can also remove this 2, because if we take LCM, then we will get x square minus z square equal to 2 times c2, and 2 times c2 is again a constant, so we can assume that a constant as capital A, or you can say that is equal to c3. So here if you want to remove this 2, then you can remove, and here we will get 3x square minus 2y square. So also we can have 3x square minus 2y cube equal to some function of x square minus z square as solution, because on taking this LCM, here we will get 2 times c2 and 2 times c2 will be another constant. In a similar way, x square upon 2 minus y cube upon 3 equal to some constant. So on taking LCM, we will get 3x square minus 2y cube equal to some another constant. So this is your complete solution of the partial differential equation 1. Now let us solve problem number 2. Auxiliary equation is dx upon p. Here you consider your p is y square. Then dy upon q is minus xy. And dz upon r, your r is x, z minus 2y. Now, if you take term first and second, on taking first and second, we get, now this y will be cancelled and we will get x dx plus y dy equal to 0. So on integration, we will get x square upon 2 plus y square upon 2 equal to some constant c, and this will be your x square plus y square equal to 2 times c, and 2 times c assume as c1. So this is your first solution. Now for the second solution, as you can see that if we take this term and this term, we will get solution in terms of y and z. So let us take part second and third. So if you take second and third, then we will get dy upon y, now x will be cancelled, equal to minus dz upon z minus 2y. So this is your collection of y and z. So now this is your, now we can write it as dz upon dy is equal to minus z minus 2y divided by y. So this is your linear differential equation of, now this will be 1 upon y and this is your minus plus 2, and in the right hand side we will get plus 2. Okay. Now this is your linear differential equation of first order and first degree. So if this is linear differential equation of first order first degree, then its solution is z into integrating factor equal to right hand side into integrating factor, then integration with respect to y plus some another constant, say c2. So integrating factor will be e to power 1 upon y dy, and 2 times integration of 1 upon y dy, then plus some constant of integration, say c2. So we will get z into e to power, this will be your e to power log y equal to 2 times e to power log y dy plus c2. As we know that e to power log x is x, so this will be your z into y, and this is your 2y dy plus some constant c2. So from here we will get zy equal to y square plus c2. So your second solution will be zy minus y square equal to c2. So this is your second solution. Therefore, our solution is phi of, say, u comma b equal to 0. Our first solution was x square plus y square, and the second solution is zy minus y square equal to 0. So this is your solution of the equation number 2, problem number 2. Then let us solve the third part. Auxiliary equation in this case will be dx upon 1 equal to dy upon 3 equal to dz upon 5z plus 10y minus 3x. Now first of all, let us take first and second. So this is your third term. So first and second implies, if you take first and second, first and second, then we will get 3 times dx equal to dy. So on integration, we will get 3x, then integration of y will be minus y, integration of dy will be y. So on the left hand side we will get 3x minus y equal to c1, and we can also write it as or y minus 3x equal to minus c1, and constant can be replaced by another constant. Say this is your c. So this is your first solution. This is our first solution. You can also write it as 3x minus y. I am writing y minus 3x because of this term. Now let us take term number 2 and 3. So on taking term 2nd and 3, let us take second term and third term. We get dy upon 3 equal to dz upon 5z. Now this y minus 3x is c. So this will be your 10c. Now here you can see that this is your function of z because 10c will be constant. So on integration we get, now the integration of y will be your dy will be y equal to, now the integration of dz upon z will be log z, but we will get 1 by 5. So 1 by 5 log 5z plus 10c plus some constant of integration, say 1 by 5 log c. We can take any constant depending on your choice. So here I am writing it as 1 by 5 log c so that we can combine these two terms. So from here we will get y upon 3, or if you write just, okay, now this will be a 1 by 5, so take this 5 here, so you will get 5y by 3 equal to log a plus log b. This will be log a into b. So this is your c1. So we will get c1 into 5z plus 10c. Now if we remove this log, then we will get c1 5z plus 10c equal to c1 5z plus 10c equal to e to power 5y by 3. Now your constant c1 will be e to power 5y by 3 into 1 upon 5z, then t, then your 10c. c was your 3x minus y. I think 3x minus y, or yes, this was your y minus 3x. So this is your second solution. Therefore, our solution is, now solution, you can write it either u equal to function of v or function of u comma v equal to 0. Say your u is y minus 3x and your v is this term. You can write it in any form and all are equivalent to each other. So I am writing in this form. So in this case, this is our solution. So this will be our solution in this case. Then I am not solving the question number 4. I am solving the problem number 5. I think it has some calculation. So let us solve 5th part. So auxiliary equation in this case will be dx upon x, then we will have z minus 2y square, then dy upon z minus qy. Okay, before writing auxiliary equation, let us remove this term. Let us reduce this term in the form of the Lagrange partial differential equation. So fifth part, this will be p into x minus z minus 2y square, then we will have this q into this term. So on taking it on the left hand side, we will get q into y, then we will get z minus y square minus 2x cube. Then in the right hand side, we will have z into this term, z minus y square minus 2x cube. So your auxiliary equation will be dx upon capital P, and capital P is x minus z minus 2y square. Then we will have dy upon capital Q. So Q, capital Q means the multiplier of small q. So this is your this term, and then finally we will have dz upon r, and here in place of r we have this term. So this is your solution. Now first term, let us take term, second term and third term. From that we will get one set of one solution. Say this is your first term, this is your second term and third term. On taking second and third, we get, so if you take second term and third term, we will get dy upon y equal to dz upon z. So this will give you log y minus log z plus some constant c. So thus our y upon z equal to c1. So this is your first solution. So we have the one part of the solution. Now let us find out another solution. For that, for the second part, now if we replace our z by, we can also write it as z equal to y upon c1. If we write 1 upon c1 as a, then we will have z equal to a times y, where my a is 1 upon c1. We can change, we can take any constant. So let us take a as 1 upon c1. So 1 upon c1 is a, so your z is a into y. Now if we put the value of z here in term 1 and 2, then you can see that 1 and 2 will be in terms of x and y. Now if 1 and 2 are in terms of x and y, and then we can solve them using the either partial, using the differential equation of order 1. So on taking first and second part, so if you take first and second, then we will get x dx upon x, then z. Let us take z as ay, and in the second term we have y, z is ay. Okay. Now from here we get dx upon this y will be cancelled. So you will get x a minus 2y is equal to, now here we will get dy upon ay minus y square minus 2x cube. So we can cross multiply these two terms. So we will get dx into ay minus y square minus 2x cube plus m into dx minus x into a minus 2y into dy equal to 0. So this is equation number 1, or okay. Now we cannot reduce it in terms of dy by dx plus by equal to q, that means in terms of linear differential equation of order 1. Now let us see whether it is exact differential equation or not. If it is exact, then you know how to find out its solution. If it is not exact, then we will find out its integrating factor. So let us suppose that it is in, let us suppose that this is of the type m dx plus n dy, where, so on comparing this equation with m dx plus n dy equal to 0, we get our m as ay minus y square minus 2x cube, and capital N will be minus x a minus 2y. So let us compute del m upon del y to check whether it is exact or not. So del m upon del y is a minus 2y, and del n upon del x is minus a minus 2y. So here you can see that as del m upon del y and del n upon del x are not equal to each other, because del m upon del y is not equal to del n upon del x. That means, say this equation is equation number A. Hence we can say that equation number A is, hence A is not exact. So equation number A is not exact. That means it cannot be, it is not integrable. In a rough sense, you can say that it is not integrable. So to make this equation number A integrable, let us find out let us first of all reduce it in exact form. So for that we need the integrating factor. Now integrating factor in this case will be, now first of all compute 1 upon n. Now 1 upon n del m upon del y minus del n upon del x. Say what is this? So this is equal to, here your n is minus 1 upon x, a minus 2y. Now their difference will be del m upon del y minus del n upon del x will be your 2 times a minus 2y. So you can see that this is your equal to minus 2 upon x. Therefore 1 upon n del m upon del y minus del n upon del x equal to minus 2 upon x, which is your some function of x. So therefore your integrating factor will be your e to the power minus 2 upon x dx. So this is your e to the power minus 2 log x, and this can be written as x power minus 2, because we can write it as e to the power log x power minus 2, and e to the power log x is x, so this will be x power minus 2. Now if we multiply this equation by integrating factor, then this equation number A will become your exact. Now multiplying A by integrating factor, we get, so if you multiply this equation by integrating factor, you will get ay minus y square upon x square, then we will have minus 2x, then here we will get minus 1 upon x, a minus 2y dy equal to 0. Now you can see that your m is this term and your n is this one. Now if you take del m upon del y and del n upon del x, then you will see that both are equal to each other. So here you can see that this equation number B is exact. Here B, so this is equation number B is exact. To check whether it is exact or not, assume this one as n and take this term as n, and then compute del m upon del y and del n upon del x, and you will see that your del m upon del y will be a minus 2y upon x square, and here your del n upon del x will be a minus 2y upon differentiation of 1 upon x, that will be 1 upon x square. That means del m upon del y and del n upon del x are equal to each other. So this equation number B is exact. Now if it is exact, so solution of B will be, solution of B is, now if you remember the solution of the exact differential equation, then it was the integration of m with respect to x taking y as constant, then integration of those terms of n free from x, and then the integration with respect to y equal to constant, say c2. The solution of this term is integration of m, that means this is your m, integration of this m with respect to x taking y as constant, and then integration of those terms of n. Here you can see that your n is this one, minus 1 upon x into a minus 2y, and those terms of n which are free from x with respect to y equal to c. So this is equal to integration of y equal to c, and then m taking y as constant, assuming as y equal to constant. Now here those terms of n free from x, you can see that there is no term in n which is free from x, because we have only one term of n and it contains x. So the integration of the second part will be your 0 into dy and equal to c2. So therefore, now integration of this one with respect to x will be, now as ay minus y square is constant, and integration of 1 upon x square will be minus 1 upon x. So we will get ay minus y square upon x, and then integration of 2x will be your x square by 2, so this is your minus x square, c equal to c2. So we can write it as ay square minus ay minus x cube equal to constant C2. Therefore, your solution is phi u v equal to 0. And your first term was y upon z, I think. And this is your y square minus ay minus x cube divided by x. So this is your second solution.